All right, good afternoon, everyone. So I think we'll get started. What we're going to do today is we're going to start chapter 4. It's our last chapter that we're going to cover. The first topic is trying to generalize what we've done so far. Every problem we've worked on up till this point has been a one-dimensional problem. So position only has an x coordinate, whether we were talking about the infinite square well or the harmonic oscillator or some kind of finite well potential. It was all a 1D problem. So we'll start by generalizing to 3D, and all of the formalism and machinery that we develop will translate in an obvious way. It's just that when we go to actually solve problems where we specify a potential and then we have to solve a differential equation, it'll be more complicated because it'll be a three-dimensional differential equation. Okay, so what we're going to do is we're going to start with our time-dependent Schrodinger equation. Nothing changes there. The Hamiltonian is still the kinetic energy term plus a potential energy term. What is different, however, is that in 3 dimensions, the square of our momentum is going to have a component along x and a component along y and z. If we were using Cartesian coordinates, for example. And we know that for the px operator, the operator is given by minus I h bar d by dx. So if I square it, the minus I becomes I squared, which is minus. So we get minus h bar squared and 2 derivatives of x. And we would get exactly the same thing for the y and z momenta as well. So we could write this as minus h bar squared, and then 2 derivatives with respect to x, plus 2 derivatives with respect to y, plus 2 derivatives with respect to z. And so here I'm writing this in Cartesian coordinates. Where we're going to go with this, the reason we want to generalize to 3D is because we would like to solve the hydrogen atom. We want to think about an electron surrounding a single proton, and then they're going to interact via the Coulomb potential. So we'll be most interested, since the Coulomb potential depends only on the distance between 2 charges, we would rather work in terms of radial and angular variables. So ultimately, we're going to write everything in terms of spherical coordinates. But to start, we'll begin in Cartesian. This sum of the squares of these derivatives is the Laplacian. And you may have seen this, I'm sure you have seen it in your E&M course. Okay, and so what we could do is we could write our square of the momentum in operator form as minus h bar squared times the Laplacian. Okay, and so that means if I go substitute that into our Hamiltonian, then we could write our time-dependent Schrodinger equation as the IH bar d psi dt, that usual thing. And then we have minus h bar squared over 2m. Now, instead of d2 psi dx2, we'll write this as the Laplacian of psi. And then that has to be, add to that the potential. Okay, so that's our 3-dimensional Schrodinger equation. 3D time-dependent Schrodinger equation. All right. One other note is that when we did normalization in 1 dimension, we took psi squared, the absolute square of the wave function, and integrated over all x. Now we have to integrate over all space x, y, and z. And so our normalization requirement becomes that the square of the wave function integrated over all space has to be equal to 1. Now, if we were to do like a dimensional analysis of this normalization, on the right-hand side, we just have 1. It has no units. So this thing on the left better be a volume. And so it has units of, say, cubic meters. And that means that the square of the wave function better have units of inverse cubic meters. So when we look at the units of the absolute value of psi squared, that has to be 1 over meters cubed. So then if I take the square root and look at just the units of the wave function itself, it is m to the minus 3 halves. Okay, so that's just something to keep in mind. All right. Now, we could do everything that we did before. One of the very first things we did in term is we said, well, okay, I don't like this time-dependent Schrodinger equation that much because it's a partial differential equation. These wave functions depend on both time and position. And what we did is we said, okay, let's try separation of variables. I'll write the wave function as a product of a position-dependent thing and a time-dependent thing. And that led to our time-independent Schrodinger equation. And that had a separation constant that was the energy. So if the potential V is independent of time, then the time independent Schrodinger equation from separation of variables becomes, okay, so minus h bar squared over 2m Laplacian acting on psi, which is now only a function of position. And I'll put like a little vector r to now indicate that this is a 3-dimensional position that we're thinking about. Plus the potential and is equal to E times psi. Okay, so the solutions are stationary states. Psi n of r, which are independent of time. They have definite energy. They're eigenfunctions of the Hamiltonian. Okay, so once we have that, the general solution to the full time dependent Schrodinger equation is, okay, so this is going to be a function of the position in 3D and time, and it's exactly what we had before. Nothing changes. There's some coefficient, Cn. There are the energy eigenstates, the stationary states, and then there was a factor, e to the minus I E n t over h bar. This last factor, remember, came from our separation of variables. We had a function of position, and we can only solve that function of position using the time independent Schrodinger equation once we specify a form of the potential. However, the function of time we could integrate right away, and we found that it had this simple form. Okay, good. So where we're going to go in the next few classes is we are going to ultimately talk about trying to solve the hydrogen atom. And so for the potential, we're going to think about the Coulomb interaction between the negative electron and the positive proton. And what we're going to try to do is we're going to try to find these stationary states. And as you'll see, it'll be a bit of work. Okay, so before we do all of that, what we're going to do is we're going to convert to spherical coordinates. The reason we're converting to spherical coordinates, as I said, is that the Coulomb potential is like some constants times charge squared divided by r. And so that divided by r means we only care about how far are we away from the origin. What's the distance between the two charged particles? We'll think of the proton as sitting at the origin. Okay, so we will be interested in the so-called central potentials. So central potentials are important also in just regular classical mechanics. They're any potential where the value of the potential does not depend on the direction that we're looking at. If I have two charges separated by a certain distance, r, the potential only depends on that distance. It doesn't matter if one charge is at the origin and one charge is, say, along the x-axis, or along with negative y-axis, or along negative x, or positive x, or along a diagonal. All that matters is that distance between them. That's what people mean by central potentials. The Coulomb potential is an example of that, and so is the gravitational potential. Okay, so where only the distance from the, let's say, origin matters. In other words, direction doesn't matter. Okay, so the most obvious example is the Coulomb potential. And so the Coulomb potential, the constant is 1 over 4 pi epsilon naught. And then if we're thinking of, say, two fundamental particles, like, say, an electron and a proton, they both have charge E. And so Q1 times Q2 becomes E squared. And then we just divide by the distance. In the case of oppositely charged particles or charges, you pick up the negative sign there. Okay. So to solve problems with central potentials, we adopt spherical coordinates, in which the Laplacian del squared is given by, okay, it's a bit of a mess. And I'm sure that you've seen this in your E&M class as well. So del squared is 1 over r squared d by dr, r squared d by dr plus 1 over r squared sine theta d by d theta sine theta d by d theta plus 1 over r squared sine squared theta d2 d phi 2. Now you can see when I stick this into our time-independent Schrodinger equation, we're going to get a differential equation, a partial differential equation That looks kind of nasty. And so we're going to try to tackle it step by step. Okay. So just like we use separation of variables to get from the time dependent Schrodinger equation to the time independent Schrodinger equation, we're going to use separation of variables to try to separate the radial and angular parts of our partial differential equations. So we will look for separable solutions to the time-independent Schrodinger equation. Okay, so our eigenfunctions that we're going to look for are going to depend on r, theta, and phi. And what we'll start with is we'll separate the r from the angular variables. Okay. Independent Schrodinger equation where the form of the Laplacian is going to be expressed in spherical coordinates. So we sub into the time-independent Schrodinger equation. All right, so let's just go back and look at that thing. Where is it? Here it is. So it's minus h bar squared over 2m. Then we have to write the Laplacian. And then for the wave function, we're going to write it as radial part r of r times the angular part y of theta phi. Okay, so let's see where that goes. So we're going to get minus h bar squared over 2m. All right. So here, I'll keep that Laplacian right there. We'll have a 1 over r squared. I'm not going to draw the 1 over just yet. I'll show you why. D by dr. And now we have to put our wave function here. But our wave function is r times y. This is an r derivative. It's only going to act on the r function. So the r derivative acts on the r function, and the y, which depends on theta and phi, can just be written out here. Okay, so that's the first term of our Laplacian. Then we have plus, we have r squared sine theta, d by d theta, sine theta, d by d theta. Okay, this time, when we put our wave function here, we have r times y, but these are all theta derivatives, so the r comes out over here. So we'll put in our r here, and our y goes there. And then we have r squared sine squared theta in the denominator, two derivatives with respect to phi. Again, only y depends on these angular variables. So I'll put a y here and an r here. Close this bracket. Okay, so all of this is just the kinetic energy term in the time-independent Schrodinger equation. We still had the potential, so we still have plus v, and then times our wave function, but our wave function is r times y now by separation of variables. And then that has to be equal to e times the wave function. Okay, good. Now we're going to employ the usual strategy. In fact, maybe what I'll do is I'll explicitly indicate that the potential depends only on r. The usual strategy is to write this in terms of a collection of things that depend only on position, and like r, and a collection of things that depend only on theta and phi. So you see, if I divide it by r, I can get all of the radius stuff out here. In fact, what I need to do is I need to get rid of the little r squared and the big R. So imagine dividing by big R divided by little r squared. then I'll get rid of these things, and I'll have things that depend only on angle. But over here, if I did that, I would still have a y here. So I'm going to divide by r times y and the little r squared, so that this becomes only a function of r. I'll package that with this thing that depends on r as well. So let's see how it all works. So we're going to divide by r times y, and we're going to multiply. I said we would multiply by r squared. Just to clean it up a little bit, I'm going to take the 2m and the h bar squared as well. So in fact, we'll do minus 2m r squared h bar squared. Okay, so let's see, what are we going to get in that case? So all of this will be gone. We divide by the y, so we end up with just a 1 over big R. And then we have a d by dr, r squared, dr, dr. Okay. I want to see if there's other stuff that's going to involve r. I divided by r times y here, so we get a vr here. But we have to remember that we had this 2m h bar squared factor, so we end up with minus 2m r squared h bar squared. And then we have v of r. And then I'm going to subtract this off and bring it to the other side. So we get a minus e. Okay, so this depends only on r. Okay, there's some other stuff left over here. These two terms are not accounted for yet. So what do we have? We have a plus. We have to divide by r times y, so we'll cancel the big R and end up with a 1 over y out front. And then what's left over, the r squared is gone because we multiplied by r squared. So it should just be a 1 over sine theta, d by d theta, sine theta, dy d theta. That's the first term, plus this one has a sine squared theta, d2y d phi 2. And all of that has to be equal to 0. Okay, and this stuff depends only on theta and phi. So if you remember the logic that we used when we were first doing separation of variables to get to the time-independent Schrodinger equation, is we said, look, we have two functions here. They depend on different sets of variables. They have to add up to be 0. So what I could do is I could go to some value of r where this equals 0, and then I could pick arbitrary theta and phi. I still need to get 0. So these have to simultaneously cancel each. Sorry, I said that wrong. I could pick some value of r, and this is going to be equal to some number. This is going to have to equal minus that number, regardless of the value of theta and phi I pick, in order for the two to add up to 0. And so they simultaneously have to be equal to the same constant. So that was the logic. So the two terms must separately be equal to the same constant, but with opposite sign. So for future convenience, I'm going to choose a particular form for that constant. It's just a constant, so I could write it however I want to. And the way that I'm going to write it is as follows. We set this constant to be L times L plus 1. Okay, so specifically, what that means is I'm going to make this R term equal to plus L plus 1. And I'm going to make this angle term equal to minus L plus 1. All right, so right now, those are just constants. We will attach some physical meaning to L a little bit later, probably Wednesday or maybe next week. All right, so notice here that when we pick a potential, it only affects the radial term. It doesn't do anything to the angular term. So we can go and try to solve this angular part right now without specifying any potential, only that it is depends only on the distance and not the direction. Okay, so what we'll do is we will start section 4.1.2, and we're going to try to attack the angular equation. So first, note that the angular equation does not depend on the form of V of R, just that it is a central potential. So this part of the derivation is valid for any central potential, not just the Coulomb potential that we'll use for the hydrogen atom. All right, so we'll write down this angular equation again. Sine theta d by d theta sine theta dy d theta plus d2y d phi 2 is equal. So we said this was going to be minus L plus 1. So what I'm going to do, let's see, can I get that on here? Yeah. So what I'm going to do is I'm going to multiply by y and sine squared theta. So we're going to put a sine squared theta here and y. But otherwise, it's just exactly that angular expression. All right. Again, if we look at this, it's still kind of intimidating because it's still a partial differential equation. It depends on phi and theta. So to simplify, we're going to do our favorite trick again. We're going to separate variables again. So separate variables again. So y is a function of theta and phi. And so we're going to say that's going to be equal to some function capital theta of little theta times another function capital phi, which depends on little phi. We do all the same stuff. We plug it in there, then we divide by theta times phi, try to find two expressions, one that only has theta dependence and the other that only has phi dependence. They have to be equal to the same constant, but with opposite sign. Okay, so we put it in there, and we'll go sine theta, d by d theta, sine theta, d by d theta. Okay, so now for y, we put this product in, and it's only going to take the derivative of that first term. So we'll put capital theta here, like so. I can do that. So capital theta goes there. So in principle, well, in reality, what I would have is capital phi here. But I'm going to divide by capital phi and capital theta, so we'll end up with another theta in the denominator. Okay, now we want stuff that involves theta. I have theta here on the right, so I'm going to move it over to the left. So the minus L plus 1 becomes a plus L plus 1, and then we still have sine squared theta. And that's it, because we're going to divide by y. And so that gets canceled. Okay, so this is one part of our equation. That's all the theta stuff. And what do we have? We just have two derivatives here. So we'll get a 1 over phi when I divide by theta times phi. And we have two derivatives of phi with respect to phi. And that has to be equal to 0. Okay, so now we're going to define our separation of variables constant. I'm going to call it m squared this time. So we'll have m squared for the theta equation, and we'll have minus m squared for the phi equation. And so this is our separation constant. Again, we will eventually attach some physical significance to this m. It's going to involve angular momentum. But it's just like when we were doing separation of variables for the time-independent Schrodinger equation, we called our separation constant E, and then we later deduced that it was the energy. So we'll later deduce what these L and M actually represent. Okay, so what we're going to do is we're going to start with the one that looks a little nicer. Let's start with the phi equation. Okay, so it's just two derivatives of phi. In fact, it's no longer even a partial differential equation. It's just an ordinary differential equation. So two derivatives of phi with respect to phi is equal to minus m squared. We had a 1 over phi, so I'll move it back over here. This should look somewhat familiar. This is just like our classical harmonic oscillator. It's like x double dot is equal to minus k squared. Okay, it's like x double dot is minus omega squared times x. Okay, so we need some kind of function where when you take two derivatives, it returns the function itself times minus some constant. And the solution is phi is equal to e to the plus or minus I m times phi. You can just check it in your head. I take one derivative, I'll get a plus minus im come down. I take another derivative, I get another plus minus m come down. They square, so I don't care about the plus minus. I get I squared m squared. I squared is minus 1, and so we get minus m squared times the original function. And so that is working. Okay. So what we'll do is we will take phi is equal to e to the plus im phi as our solution and allow m to be positive or negative. Okay. you could complain that there should be some overall integration constant here. But what we're going to do is because, where is it? Because y is going to be equal to the product of two functions, I can just absorb its normalization constant into the theta function. Okay, so we still have overall normalization to worry about, but we'll worry about it when we do the theta equation. All right. Before we finish this off, I want to look at some restrictions on M. So for spherical coordinates, we require that if I take phi to phi plus 2 pi, the function, or if you like, the state, is unchanged. So remember, spherical coordinates, we have, say, a z-axis, then theta is measured from the z-axis. So this would be theta equals 0. If I have my theta horizontal, that's theta is pi by 2. And then when it's pointing down, that's theta is pi. And that's the full range of theta. Theta goes 0 to pi, and it's measured relative to the vertical z-axis. Phi is the azimuthal angle, and it goes around 0 to 2 pi. So if you start, say, on the x-axis and then rotate, I guess which way, if you're looking from above, we'll rotate through 2 pi, and I'm back to my starting point. And so it better be that if phi is translated by 2 pi, we better get the original function back. So our capital Phi function of little phi, has to be equal to little phi plus 2 pi. Okay, but we just said that our function was going to be e to the im times phi. So that has to be e to the im phi plus 2 pi. But then I can separate this exponential of a sum into a product of exponentials. E to the im 2 pi. Okay, good. So, well, okay. If I do this carefully, e to the im phi is equal to e to the im phi is equal to the, I don't know, e to the 2 pi I times, times e to the 2 pi I times m. But I can cancel a common factor on both sides, and that means 1 is equal to e to the 2 pi I times m. But remember, Euler's equation says I can write these complex exponentials as cos of 2 pi m to plus I sine of 2 pi m. And so what I need is I need the sine to vanish, and I need the cosine to be 1. And the only way I can do that is if m is integer. If I put in m is 0, it works. If I put in m is 1, it works. M is 2 works. M is minus 1 works. M is minus 2 works. And so all integer values of m work. Anything not integer doesn't work. So this works only if m is integer. Okay, so m could be 0 or plus or minus 1, plus or minus 2, and so on. Okay, so that's what we know so far. What we're going to have to do now is we're going to have to go and think about the more difficult problem, and that is the theta equation. And so let's see if we can make some progress here. the theta equation. Now, before we get too far into it, remember when we were doing the quantum harmonic oscillator, we solved it in two ways. We first solved it with this like a hat plus minus operators. This was like where we kind of thought about trying to factor the Schrodinger equation. But then we went and we repeated everything. And we just started with this differential equation. We assumed some kind of power series solution. We plugged it into the differential equation. That led to a recursion relation in the coefficients of different powers of x, for example. So that's the sort of approach that we'll adopt here. So theta equation, sine theta. In fact, we won't actually do all of the steps for this theta equation. We're just going to appeal to what we've already seen before. So I'm just writing the theta equation out again. Okay. All right. So I'm going to just rearrange this. Let's see. In fact, I'm not going to do much rearranging. I'm going to multiply by the big theta, get it out of the denominator. So the first term, in fact, again, I don't have to write partial derivatives anymore. This is an ordinary differential equation. So there's the first term. I'm going to subtract off the m squared. So we get a plus. We have L plus 1 sine theta. In fact, I must have written, let's go back and look. I think I dropped a squared. This is L plus 1 sine squared theta. So this has to be a sine squared theta here. And this is a sine squared theta. All right, then I'm going to subtract off the m squared. And remember, we had to multiply by the big theta. And then all of that's equal to 0. Okay. So this looks a little messy. I'm going to do something that Griffiths doesn't do. I'm going to do a little aside here. I'm going to manipulate this. And we're going to do this manipulation as a way to connect it back to one of the problems that you did in your homework, or at least you were asked to do in your homework. So in the homeworks, I have like the graded questions and then the recommended questions. One of the recommended questions was to try to solve the differential equation that's related to this one. So let's see how that works. We're going to set m equal to 0, and I'm going to divide by sine squared theta. Okay, so m equals 0. So we're going to ignore this. This little aside is not the differential equation that we need to solve, but we're going to get to a related one, which is useful to see. So m equals 0, divide by sine squared. So this is gone, and we're going to have a 1 over sine theta in the first term. So 1 over sine theta, d by d theta, sine theta, d theta, plus L plus 1 theta is equal to 0. Okay, so I'm going to make a change of variables. If x is equal to cos theta, then dx is equal to what? Minus sine theta d theta. And that means that d theta dx is equal to minus 1 over sine theta. Okay, so we can see some of that stuff here. So what I want to do is, let's see 1 over sine theta d by d theta. Well, what am I doing? I see. So, okay. So 1 over sine theta is like minus d theta dx. So this is minus d theta dx. Whoops. And then we have a d by d theta. But this is just like chain rule. This is chain rule for d by dx. This is minus 1 over d by dx. This is chain rule. So that's going to simplify this thing quite a bit. Okay. Well, what about d theta dx? What if I wanted to evaluate something like that? Well, that would be d theta dx d theta d theta. This is kind of a chain rule written in a more conventional way. But we already said d theta dx is minus 1 over sine theta. And so therefore, let's see, well, okay, well, let's put this on the next page. This is minus 1 over sine theta, d theta, d theta. And so therefore, d theta times sine of theta is equal to, let's see, whoops, is that what I wanted? No, okay. I'll just leave it like that. Or no, maybe I won't. So let's solve for d theta, d theta. All I'm going to do is multiply by sine theta and the minus sign. So that's equal to minus sine theta, d theta, dx. Okay, so let me show you why I wanted to do this. So what we're going to do is here, we're going to replace all of that with minus d by dx. And here, we're going to replace that thing. Oh, why isn't my pen working? Oh, I don't know what's happening here. Oh, good. What happened? Yeah. Okay. Good. So those are the two substitutions I'm going to make. Let's see what happens. So therefore, we have a minus d by dx. And then we have sine theta. But then we have to multiply by minus sine theta. So when we multiply by minus sine theta, the minus sign cancels and we get sine squared. And then we have d theta dx. And that's equal to, okay, that's equal to L plus 1 times theta. Okay, good. The next thing we're going to do is we're going to say, well, let's write sine squared theta as 1 minus cos squared theta. Okay, so then we have d by dx of 1 minus cos squared theta d theta dx is equal to plus, sorry, I keep screwing up. This is plus, and then this equals 0. So this is plus L plus 1 theta, and that's equal to 0. Okay, but when we make this change of variables, we said x was equal to cos theta. So this is really 1 minus x squared, since x was equal to cos theta for our change of variables. And so now we have something where we could actually evaluate this derivative and make some progress. So therefore we have, I'll write it out, d by dx of 1 minus x squared d theta dx plus L plus 1 times theta is equal to 0. Okay, so now we're actually going to do the derivative, and it's product rule. So let's see, we get, therefore, minus 2x d theta dx plus 1 minus x squared d2 theta dx2 plus L plus 1 times theta is equal to 0. All right. And this is what I wanted to get to. This is Legendre's equation, and your recommended homework was to plug in a power series solution. So it would be something like a0 plus a1x plus a2x squared plus a3x cubed and so on. Then you evaluate these derivatives. So just simple like power law derivatives. And you would come up with some relationship between coefficients of equal powers of x. Okay, so Legendre's differential equation so this is the m equals 0 case that we're not working on, but if we took the m equals 0 case of ours, it would lead to 1 minus x squared d2 theta. I'm just writing down the exact thing we just derived. I'm just reordering the terms. Okay, good. So actually, I could tell you the exact recommended problem it was. So recommended problem from chapter 2, it was problem 2.64. So the solutions to Legendre's equation are the Legendre polynomials. So they're denoted PL of x. It's just like for when we did the quantum harmonic oscillator, we had to derive these Hermite polynomials. So this is just another set of polynomials. Okay, so what you would do is you'd sub in a power series solution. Then you would find a recursion relation for coefficients. Of powers of x. And then what you would have to do is you'd have to truncate the recursion relation to stop it from diverging. And if you do all those things, it leads you to the solutions for these Legendre polynomials. And the solutions, the first few of them are P0 is equal to 1, P1 is equal to x, P2 is equal to 1/2 of 3x squared minus 1, and so on. There's actually a pretty easy way to generate all of the Legendre polynomials if you know the first few. So PL of x can be generated from the Rodriguez formula. And it looks like this. It's 1 over 2 to the L factorial, and it's the Lth derivative of x squared minus 1 to the power L. So we could do some of these easily in our heads, right? Let's take L equals 0. L equals 0, we get 2 to the 0 times 0 factorial. Both of those are 1. So all of this is 1. And then we take the 0th derivative. So we don't take any derivatives. X squared minus 1 to the power 0 is just 1. So that clearly works. Let's do L equals 1. So this is going to be 1/2. First derivative of x squared minus 1 is 2x times the 1/2. And we get the x. And then you could keep going for L equals 2 and 3, and as long as you care to continue. What you'll find is that all the even L's are even functions of x. And so if we went to p to the 4th, we would have an x to the 4th term and an x squared term. If we went to p to the 6th, we get an x to the 6th term, an x to the 4th term, an x to the squared term. So they're even powers of x up of order L. All the odd ones are going to be all the odd powers of x up to order L. Okay, good. Now, let's get back to the equation that we're actually trying to solve. So the solutions to our differential equation, which I'll rewrite again. Sine theta d theta, sine theta d theta plus L plus 1. Then there was sine squared theta minus m squared. Can't set m equal to 0 for our case. Okay, now the solutions to this are the so-called associated Legendre functions. Okay, so the solutions to our, so the solutions are given by, so our solutions are this capital theta. And it is equal to, let's do it like this, PLM of x, which are called the associated Legendre functions. Now, we're not going to do it, but we could attack it in the same way. What we would do is we would try to sub in some kind of power series solution. We would evaluate those derivatives, and we would look for relationships between coefficients of like powers. That's going to lead to a recursion relation, and we're going to have to truncate the recursion relation by picking some value that kills the recursion beyond some maximum value of m. Okay, the solutions, what they actually look like are as follows. So it's -1 to the m, and then it's 1 minus x squared to the m over 2 d by dx m. So the mth derivative of the regular Legendre polynomials. So you need the Legendre polynomials to generate the so-called associated Legendre functions. The reason it's called an associated function and not an associated polynomial is because if I put in m odd, like just try m equals 1, then we get the square root of 1 minus x squared. And that's not a polynomial like a0 plus a1x plus a2x squared. The square root throws it off. Okay, so this thing is because of this factor, PLM of x is polynomial for m even, but not for m odd. Okay, so let's do an example. Okay, so P2, 0. Well, what would we do? So this is L equals 2 and m equals 0. So if I put in m equals 0, I get -1 to the 0, and I get 1 minus x squared to the 0, and I get the 0th derivative. And so that's easy. In fact, with m equals 0, this is just equal to the second Legendre polynomial, and we wrote that down already. It's only when m is not equal to 0 that we get something different. So P21 of x, well, let's see, it's going to be -1 to the 1. And then it's going to be 1 minus x squared to the 1/2. And that's going to be the first derivative of the second Legendre polynomial. And so that's going to be 1/2 3x squared minus 1, like so. And then so we could actually do this. It's minus the square root of 1 minus x squared. And then let's see, the derivative of 3x squared is 6x. We have a 1/2, so we get a 3x. And so what it ends up being is -3x, the square root of 1 minus x squared. And you can clearly see from this example that this is not a polynomial because of the square root. So that's why they're called associated Legendre functions, because they're not always polynomials. So a couple things to note here is that this works only for m greater or equal to 0. So m has to be positive, right? What does it mean to take the -1 derivative of some function? So this is only defined for m positive, but we said that m could be 0, plus -1, plus -2, plus -3, and so on. So we need to have a way of deducing what we would get for m less than 0. So for m less than 0, we use the relationship PL minus m is equal to -1 to the m, L minus m factorial, L plus m factorial, PLMX. So let's do an example. So like this. So let's do, we've been doing the L equals 2 case. Let's do L equals 2, M equals -1. Okay, so really, this is like M equals 1, and then we pick up a minus sign here. So this is -1 to the 1. So it's -1 to the 1. And then it's L is 2 minus 1 factorial divided by L is 2 plus 1 factorial. And then this is P 2 plus 1 of X. Okay, what do we have? We get a minus sign. And then we get 1 factorial, which is 1. 3 factorial is 6. So we get -1/6 of P L equals 2, M equals 1. We already worked that out. It's -3x square root of 1 minus x squared. And so let's see, the minus signs cancel. We have 3 over 6 is 1/2. And so this is 1/2 of x root 1 minus x squared. So you could see that actually the functional form for m equals plus and minus are the same. It's the same x square root of 1 minus x squared. The only thing that's different is possibly a sign change and some overall prefactor. Other than that, they look similar. All right. So we're going to do one more thing that's actually going to make this a little more simple. So let's note that the Legendre polynomials are defined on the domain x spans -1 to +1. In fact, you could see if we go back and look at some of these Legendre polynomials, where are they? Did we write some down? Yep, here they are. 1, 1, and 3x squared minus 1. So if I put in x equals 1 or -1, I get 1 and -1. Over here, I would get 3 minus 1 is 2 times 1/2 is 1. So the Legendre polynomials are defined to be finite on this interval -1 to 1. In fact, they always terminate on plus or -1. You could see, obviously, if I took x to be plus infinity or minus infinity, these are going to diverge. So in order to make them normalizable, the domain is restricted. But actually, the -1 to +1 is sort of a perfect domain if you think of, we're doing cos theta for the theta dependence of these wave functions we're trying to work out, these stationary states. But theta goes from 0 to pi, and so that means cos theta goes from cos of 0 is 1, and cos of pi is -1. So it exactly falls on this range. So it was no accident that I made the change of variables x equals cos theta above. And we're going to do that again. So defined on the domain -1 to 1, this corresponds to x equals cos theta, where theta spans 0 to pi. So these Legendre polynomials and the associated Legendre functions are natural functions or polynomials to describe some angular dependence. Okay, so furthermore, in this case, the factor 1 minus x squared simplifies to 1 minus cos squared theta. Well, that's just sine squared theta. Okay, so let's see. P20 of cos theta. Well, what's that going to be? We said 2P0 is here. Okay, so if we put in cos theta for x, we just get 1/2 of 3 cos squared theta minus 1. So 1/2 of 3 cos squared theta minus 1. One that's a little more interesting to look at is P21. So what did we have for P21? Here it is, minus 3x square root of 1 minus x squared. So it was minus 3x. So I put cos theta for x, square root of 1 minus x squared. So I put cos theta for x. But this is square root of sine squared theta, which is just sine theta. And so this is equal to minus 3 cos theta sine theta. And likewise, P2 minus 1, if you work it out, will be 1/2 cos theta sine theta. And you could keep on going like this. All right, we have a couple minutes left, and I want to do one more thing. You'll often see people plot these functions, and they plot them in a way that you wouldn't normally assume they would plot them. Like if you look at this function, you would think of plotting PLM as a function of theta. So you have your Legendre function on the y-axis and theta on the x-axis, and you just span theta is 0 to pi. You could absolutely do that. But what people will often do is they will show polar plots. Polar plots of PLM cos theta. So the way they generate these polar plots is they say, okay, I'm going to define some R, and it's going to be the absolute value of these associated Legendre functions. And what we'll do is we'll find some coordinate system, x, y, and I'm just going to make polar plots. So I'm going to plug in a value of theta to this expression, and I'm going to find the length of r. So this is going to be r, and then I'll put a point at the end of my little r vector, or my r line. So let's do an example. So we're going to plot a point at the tip of r for all theta from 0 to pi. So it's easiest if I show you an example. So let's take, for example, P21. We worked out P21. It was minus 3 cos theta sine theta. So I'm going to make a table. And so I'm going to pick values, theta. I'll pick some common angles where we can know without too much trouble how cos and sine evaluate. 3 pi by 4, 5 pi by 6 pi. So this is just some select angles. Let's imagine that we made a really huge table where the increment between theta values was really small. So we get this continuous sort of range of theta values. All right, when I put in theta equals 0, I know sine of 0 is going to be 0. So I'm going to get a 0 here. When I put in theta equals pi, I know sine of pi is going to be 0. So I'm going to get 0 here. When I put in pi by 2, I know the cosine is going to be 0. So I get 0 here. So there's some easy values. When I do pi by 4, cos theta and sine theta are equal. They're both equal to 1 over root 2. So I'm going to get minus 3 times 1 over root 2 times 1 over root 2. And so that's going to be minus 3 halves. When I go to 3 pi by 4, cosine and sine are equal but have opposite sign. They're both equal to 1 over root 2. The sine is plus 1 over root 2. The cosine is minus 1 over root 2. So we get minus 1/2 times minus 1/3. So we get plus 3 halves. Times minus 3. So we get plus 3 halves. So for some of these other ones, like the pi by 6 and stuff, you get factors of one of them gives a 1/2 and one of them gives a root 3 over 2. And so if you actually put in the numbers, you get minus 1.299 in a couple places, and you get plus 1.299 in a couple places. All right, and so I want to try to do this polar plot that we said we were going to try to construct. And this will be the last thing we do today. All right. So what I'll do is I'll go to an angle of 0. An angle of 0 on my, if I measure from the horizontal axis, is a point on this axis. And so we're going to get 0 there. And then I go to an angle of pi by 6, that's 30 degrees. And I say, well, the length of my vector is 1.299. It's 1.3, essentially. So what I'm going to do is I'm going to say, okay, 30 degrees is something like this. And maybe that is from the origin to this point, we'll say is 1.3. So this is 1.299, and this is pi by 6. So there's 1 point. And then I go, okay, I go pi by 4. That's 45 degrees. And then I'm at a length of 1.5. So we go to 45 degrees, and we're a little bit further away. And then we go to here, would be 60 degrees. And 60 degrees is back to the 1.3 length. And so 60 degrees is somewhere like along here, something like that. All right. And then we say, all right, if I go to, oh, I should have did this differently. All right. Okay, let's back up. How much time do we have? Oh, I'm already over time. What we'll do is we'll fix this plot, the first thing, next time. What we were doing is fine. I just want to measure the angle from the vertical axis so that it looks more like spherical coordinates. I was measuring from the horizontal axis. We'll repeat it where we measure from the vertical axis next time, and we'll make a plot, a polar plot of this Legendre function. All right, so that's where I'm going to stop. Thank you very much. So we are almost done solving the angular part of our wave function. Next time we'll finish it off, and then we'll start working on the radial part. Okay, perfect.